The landscape of artificial intelligence is, well, it's quite literally shifting under our feet right now. If you've been paying attention to how production AI systems are actually getting built, you've probably noticed a massive pivot away from just tweaking words. So, in this explainer, we are unpacking the actual technical standard for building reliable production AI systems in 2026. It's called loop engineering. And honestly, by the time we're done here, any confusion you have around how to actually make AI agents work in the real world is going to completely disappear.
To get us there, here's our mental roadmap. We're going to cover 6 parts today: the paradigm shift, anatomy of the loop, harness engineering, context budgeting, verification in the loop, and finally, nested loop design. Let's just jump right in.
All right, starting with part 1, the paradigm shift. To really understand where we are today, we kind of have to look backwards at how the primary bottleneck in AI development has evolved over the past few years.
Think back a couple of years ago. The absolute highest leverage skill was prompt engineering, right? Models were pretty rigid, so you had to meticulously craft the exact wording of your input. It was almost an art form. Then, models got better, and the bottleneck shifted to context engineering. It stopped being about the exact phrasing and started being entirely about what the model could actually see at inference time, curating those retrieved documents and memories right into the context window. But now we've entered the third era, loop engineering. Because models can write their own prompts and pull their own context through tool calls, the input itself just isn't the scarce skill anymore. The scarce skill is designing the execution cycle itself. So what is loop engineering exactly? Simply put, it's the deliberate design of the cycle an AI agent runs inside. You're figuring out what does it do between steps, when does it check its own work, what happens when a step totally fails. You're no longer handwriting every individual step, you're engineering the act, observe, verify, and retry cycle. To make this super concrete for us today, we're going to use a running example throughout this explainer. Imagine an AI customer support agent for an online store, one that specifically handles refunds and checks shipping statuses.
Okay, moving right along to section 2, anatomy of the loop. We're going to tear apart the actual primitive mechanism sitting underneath every single functional AI agent.
If you've ever heard of the React pattern, this is literally it in action. Think about our customer support agent processing a user's message. First, it reasons. It classifies the intent of the incoming message as, say, a refund request. Second, it acts, maybe by calling an internal order lookup tool. Third, it observes, as the order record comes back and gets appended to its context. And fourth, it repeats, perhaps checking that requested refund against company policy before finally drafting a reply. Each of these steps is just another pass through the exact same loop.
Now, here is an absolutely crucial part. The single most common failure in production is missing stopping conditions. When does the loop actually end? Without these conditions, you end up with a runaway agent that just spins its wheels, calling tools in an infinite loop and racking up an API bill that will literally make your CFO cry. You need explicit termination. That could be a clear done signal from the model, a hard cap on the number of iterations, a strict cost or token limit, or passing an automated verifier. Actually, you usually want several of these running at once, because let's be honest, you simply cannot fully trust a model's own sense of when it's finished.
And the economics here are just brutal. Every single iteration is a full model call. If you've got an agent that takes 10 steps to complete a simple 2-step task, it isn't just a little bit slow. It multiplies your inference bill by 10, and it multiplies the surface area for something to go horribly wrong by 10. So a huge part of loop engineering is minimizing those unnecessary iterations by giving the model the perfect context and tools right out of the gate.
All right, section 3, harness engineering. Let's shift our focus to the unseen foundation that actually keeps these loops from falling apart under real-world pressure.
There is a reality that most people completely miss when building agentic systems. We so easily get mesmerized by the unpredictable creativity of the AI, but that model magic, it's only about 5% of the equation. The other 95%, that is the harness. A production agent only survives because of traditional boring software engineering. The harness is the deterministic code tightly wrapped around the model. It's the retry logic when a tool fails. It's the timeout when a database is lagging. And it's the strict guardrails that stop an agent from promising a customer an unauthorized refund. Ultimately, the harness is what decides if this thing can actually ship.
And because of this, how you evaluate your AI has to change completely. You aren't just looking at a generated reply and asking, is this a well-written sentence? No, you are grading a system under stress. Teams that actually ship reliable agents use tracing tools, things like Langsmith or Langfuse, to score end-to-end runs. They test exactly how the system degrades gracefully when an API suddenly goes down, or how it handles a weirdly malformed input, or even a super angry customer.
Which brings us to Section 4, Context Budgeting. So, what exactly happens to our agent's memory as these loops run over long periods of time?
Well, if you've ever watched an agent start out super strong and then just completely hallucinate or lose the plot halfway through a task, you've experienced this pain firsthand. It's called context rot. As the loop iterates, every single tool result and reasoning step gets appended to the context window. On a really long task, the model's quality measurably degrades as that window fills up with stale, low-signal tokens. It just gets overwhelmed.
Context is a resource you absolutely must actively budget. You manage this rot through a few key techniques. First, compaction, creating periodic, short-running summaries so the model keeps the main thread without carrying every raw token. Or you might use external memory, writing facts out to a database and retrieving only what's currently relevant. And crucially, you need strict tool result management. If an order lookup returns thousands of rows, you don't just dump that into the model, you filter and extract it first. In fact, spinning off a sub-agent for a specific task is often just a really clever context management strategy to keep your primary loop lean and focused.
All right, Section 5, Verification in the Loop. This right here is the absolute hinge that the entire loop turns on. There is a massive asymmetry in how we verify AI outputs. On one side, we have cheap automated verifiers, like checking if a piece of code actually compiles, or verifying a basic deterministic rule, like making sure a refund is under $100. But on the other side, we have subjective verifiers, like judging if a refund exception was reasonable, or doing a subtle tone check on an email. The golden rule here is that whenever a check is cheap and automated, it belongs squarely inside the loop, so the agent can catch its own mistakes and self-correct on the fly.
Which naturally leads us to this quote. And it's a golden rule for design. Verification is what tells you where automation ends and where human review starts. It is a highly deliberate design decision. Whenever you don't have a cheap verifier and the judgment required is genuinely subjective or novel, that is precisely where a human belongs in the loop.
Finally, Section 6, Nested Loop Design. Let's zoom out from the active agent itself to look at the macro design patterns tying this whole software engineering process together.
This brilliantly maps to Andrew Ng's concept of 3 nested loops in software building, which all operate at totally different speeds. First, you have the agentic coding loop. This runs in seconds or minutes, driven by an AI constantly testing its own work against a spec. Second is the developer feedback loop, running in tens of minutes to hours, driven by you steering the agent and updating the rules. And finally, the external feedback loop, running in hours to weeks, driven by real customers and live production data. Notice how, as you move outward in time, verification relies increasingly on human judgment rather than automated tests. Humans don't disappear in this new world. They just move to where they have the ultimate context advantage.
And this ties the whole shebang together beautifully. Take a look at how Andrew Ng's 4 original agentic design patterns aren't just theory. They are the literal building blocks of our support agent's loop. Reflection? That's the verifier checking the draft against the refund policy. Tool use? That's executing the order lookup. Planning? That's sequencing the classify, lookup, and respond steps. And multi-agent collaboration? That's spinning off a sub-agent to safely handle a specialized task. It is all perfectly connected.
So as we wrap up this explainer, I want to leave you with a real brain teaser to take back to your own projects. Stop polishing isolated components and just hoping the system sorts itself out. You have to look at the whole loop. How is your engineering team deliberately budgeting its iterations, cost, and context for the next generation of AI? Because I promise you, the teams that master the loop are the ones who are actually going to ship reliable AI in 2026. Thanks for hanging out with me today, and keep exploring.